Welcome back. I'm doing the second half of Chapter 8 just a few hours after I did the first half because I feel like they kind of hang together, so I wanted to do them. Usually I do these one day at a time, but I'm doing these all in one day because it just feels like one big story. So let's practice from last time. Electrons belong to the what family, which is why they only go into quantum states two at a time. So think about that. Answer is they're fermions. We'll discuss a little more today what that actually means. The fuzzy ball pictures of atomic electrons represent what kind of psi waves? Standing waves. That's right. I'm going to shift this camera here. They're standing waves. I told you that light is emitted when charges are wiggled, moving electric fields up and down. Now, what photon picture should we have in our heads when a charge gets wiggled to make an electromagnetic wave, which is made up of photons? Which of these is the best picture for what's happening when you wiggle a charge up and down and make photons? I guess you could argue about this some, but I think the one that makes the most sense, probably the one that you ought to have in your head, is A. You wiggle a charge up and down, and photons are shaken out, going at the speed of light, like salt from a shaker. How about this one? Photons are emitted from atoms, and electrons make a transition from which of these? And its higher energy state to a lower energy state. The electrons lose energy, and that energy shows up as a photon. Okay, I'm going to talk about quantum numbers, about spin, and the periodic table today. A little bit of housekeeping. There's a sample final posted. It's like the one you'll take. In fact, I had a big final that a friend of mine used a long time ago. He's the one who taught me how to teach this class. I thought it was too long, so I took all what I thought were the harder questions of his final and put them in the sample. And you're going to take the easier half, but probably not easier by much. There are 30 conceptual questions, meaning is something bigger than something else, smaller than something else? What does something mean? 30 like that, multiple choice. And then there are 11 numerical problems with multiple choice numerical answers for you to choose. You might try this. This has to do with electrons falling down from a high energy state to a low energy state. If you can look this up on YouTube, or you can do it yourself. You take a wintergreen lifesaver, you put it in your mouth between your front molars, go into a bathroom, look in the mirror, and make sure you can see where that wintergreen lifesaver is in your mouth with your mouth open in the mirror in the bathroom, and then turn the lights off and bite it. And when you bite it, it will glow green. You'll see green light come off that wintergreen lifesaver when you crush it. The force of your bite excites some atoms, and they emit photons. This has also been used as a fun date activity in the past. There's an effect called phosphorescence, which some of you may know about. It's things that just glow in the dark for a long time. One of my kids put phosphorescent stars up on her ceiling in her bedroom. So when she'd go to bed and lay down in her bed and look at the ceiling, it would be completely covered with stars, and the stars lasted for many minutes. Some atoms, when you put them in an excited state, will stay in that excited state for a long time, only slowly emitting photons. And that makes them glow in the dark. There was this beautiful experiment just a few years after Bohr's theory of the atom, which we talked about last time. Some measurements have been made on atoms since then that once the idea of excited states and light coming out at the frequency corresponding to the energy difference between the higher energy state and the low energy state. And it was known that mercury had its first excited state at 4.9 eV. In the Franck-Hertz experiment, they took a dilute gas of mercury and they shot electrons into it. Electrons with, at first, very low energy, and then gradually increasing the energy to 1 eV, 2 eV, 3 eV, 4 eV. When the electron energy got up to 4.9 eV, which is essentially 5 eV, all of a sudden, the speed of the electrons going through the gas went way down. They didn't notice the light coming out of it. Well, yes, they did. There was light coming out of the gas. 4.9 eV photons started to shine out of the gas, and the electrons slowed down. What was happening was that the electrons were giving their energy to atoms to pump them up into the excited state, and then they could emit light. But it slowed the electrons down, and there weren't as many electrons, and they weren't going as fast. When Einstein saw the results of this experiment, he said, "It's so lovely it makes me cry." I'll show you the picture that made Einstein want to cry. But before we do that, let me talk to you a little bit about facts and theories. It was a fact that when you shot these electrons into the mercury gas at different energies, that sometimes light came out and sometimes it didn't, and sometimes the electrons slowed down and sometimes they didn't. Those were the facts. And everybody who had the skill and the equipment to reproduce this experiment would get the exact same answer every time they did it, as long as they didn't make a mistake. That doesn't tell you what's going on. A theory is a story about facts. Good theories connect the facts together into one great whole, and once you have this big, beautiful story that connects a whole bunch of facts, it usually suggests new experiments you might try to see what some new facts might be. So I believe in science as far as it has been translated correctly. I believe in the stories as long as they agree with the facts and until a better story comes along. It's kind of like a several thousand piece puzzle with evolving stories or theories about how the pieces fit. And if you're a storyteller, a scientist, theoretical scientist, you'll get a prize if you find a better way to make the puzzle pieces fit that predicts facts that can be tested by experiments performed by anybody with the equipment and the skills. And if a theory fails a test, even one test, then we start over. So here's the Franck-Hertz experiment. These are the facts. You can see that as the voltage accelerating the electrons was increased, that the current collected through the gas went up. Current means either electrons are going really fast, or it might mean lots of electrons. Either way, you'll get more current. So as you put an accelerating voltage on the electrons, probably you were making about the same amount, but they're going faster, and so you collect more current until you get to just below 5 volts of accelerating voltage, and then all of a sudden the current goes way down. You can accelerate it again, and then when you get up around 10, just below 10 volts, after it started increasing again, it goes down again. So there ought to be a story you could tell about this. And the story is the story of atomic energy levels. So when the electrons have an energy in the neighborhood of the first excited state of the mercury atoms, then when an electron hits a mercury atom, instead of just bouncing off like it normally does at low energy, it gives its energy to the mercury atom to promote an electron up into the first excited state. That makes the electron slow way down, decreasing the current, and a photon would come out, so the gas starts to glow. As you continue to accelerate the voltage, those slowed down electrons will start to speed up again, and they speed up and they speed up and they speed up until you're at twice the excited state energy. And now you have electrons that have already interacted with an atom once and lost their energy, but now they've gained another 4.9 volts of energy back, and they give their energy to the mercury atoms again, and so it drops again. And it happens at about 3 times the excited state voltage. It's just a really beautiful verification that the first excited state of mercury has an energy of 4.9 eV. Okay, so just as we found 3 quantum numbers for each state in a particle in a box, Schrodinger found 3 quantum numbers for the spherically symmetric attractive electric force of the nucleus, and he did some beautiful and complex mathematics and came up with Bohr's formula that the energy levels in this simple 1 electron atom, which is hydrogen, that the energy levels are given by minus 13.6 eV divided by n squared, the first quantum number squared. In Schrodinger's theory, the energy doesn't depend on the other 2 quantum numbers. That's not like particles in a box. It's special to spherically symmetric attracting potentials. So the energy doesn't depend on L or M. Schrodinger's 3 quantum numbers are integers, but there are rules about them. They can't just be anything you like. So here are the rules. You count n, 1, 2, 3. That's the principal quantum number. It tells you how many radial wiggles there are in the standing wave function for psi. So you go 1, 2, 3 with n. Once you've chosen an n, then L can be either 0 or 1, and you keep going up until you get to n minus 1, and then you have to stop. You can't have any L's beyond n minus 1 once you've chosen n. Once you've chosen L, then there are also possible values of m, and those possible values are minus L plus 1, up to 0, and then on the way up to L minus 1, and then finally L. So here's an example. If n is equal to 1, then n minus 1 is 0, and so you can only have L equals 0. And because you can only have L equals 0, you can only have M equals 0. So this is a pretty simple energy state. There's just one of them. If you go to n equal 2, the next energy level up, then you can have L equals 0. That's legal. And then M equals 0 goes with that. But you can also have L equal 1 because n is 2 and 2 minus 1 is 1. And so now with L equal 1, M can be minus 1, 0, and 1. So in the n equal 2 level in the hydrogen atom, you have a state at n equal 2, and you have 3 states. You have 1 state at L equals 0 for n equal 2, and you also have 3 states at L equal 1. So there are 4 states altogether in the n equal 2 level. All right, so I'll let you do one of these. For a hydrogen atom, when n equals 2, the lab values of L and M are, so what can you have for L? Of course, it's not too hard, we just did this. I guess you could rewind the clip and look up the answer. Well, it's A. L can be either 0 or 1. If it's 0, you can only have M equals 0. And if it's 1, you can have minus 1, 0, and 1. And then as you go up to n equal 3 and 4 and 5, it proceeds similarly. For historical reasons, which we shouldn't have to worry about today, but unfortunately these names stuck and we still use them today. L equals 0 is called S, and L equals 1 is called P, L equals 2 is called D, and L equal to 3 is called F. Okay, well, this is a lot of detail about the hydrogen atom, but there are 92 elements. I mean, why would we think that whatever happens for hydrogen would have anything to do with what happens for helium, lithium, boron, beryllium, all the rest? Who cares? Well, what happens is that electrons, as you increase the number of protons in the nucleus, so that you have to have more electrons around the atom, the electrons go into the lowest energy states, but they don't all go into the lowest one because they're fermions. You can only put one electron in a quantum state, counting its spin too. We'll see that that means in a state with, if you have one state, you can have 2 electrons. If you have 4 states, you can have 8. If you have 10 states, you can have 20, etc. Or 5 states, you can have 10. So what happens is, as the electrons go into these lower energy states, they fill up. It's like coming into an auditorium and everybody sits on the front row, and now once you're sitting on the front row, nobody else can sit in that seat. And so the crowd fills up going toward the back of the room, and if somebody comes in late, they have to sit in the back. But these aren't just people, these are electrons. And so if you have, say, 20 protons, then 19 of the electrons will be in fairly low energy levels. And the 20th one, when he shows up, he's got to sit in the back. And so when he looks at this atom, and he's on the outside, he sees 20 protons and 19 electrons, and that adds up to 1 positive charge. And that's what he mostly interacts with, is this 1 positive charge. Well, that's like a hydrogen atom. It's an electron and 1 positive charge in the middle. Now, that's not quite true, because those other electrons that are close to the late coming electron, well, they're going to repel that electron, and that messes the energy levels up. But it doesn't mess them up so much that you can't call them by their hydrogen names. And so that's why it makes sense in talking about atoms to pretend like they're all the electrons are fitting into the hydrogen quantum states, and then we take care of the exceptions by making exceptions. Okay, so atoms, the atoms that you're used to, have new names now. We name them by their principal quantum number, n, by their L, using S for 0 and P for 1 and D for 2 and F for 3. And so hydrogen is called 1s1. It means that you're in the first principal quantum number level, n equal 1. It's an S state, which is L equals 0, and you have 1 electron in that state. Helium is 1s2. Again, it's n equal 1, principal quantum number is 1. It's an L equals 0 state, that's what S means, and there are 2 electrons in it. Okay, so you might think then that lithium would be 1s3. That's the next atom in the periodic table, 3 charges, 3 protons. But there is no 1s3 because this crazy thing called spin shows up. Some quantum particles just have spin, like they have mass and charge. It's a fundamental property, and it means angular momentum, and they just have some for no apparent reason, like a spinning top that never slows down. So an electron, for instance, has mass, and it has charge, and it has spin, and the spin is fundamental. And the spin of an electron is 1/2, meaning it has 1/2 h bar of intrinsic angular momentum. If you apply the M rule to S equals 1/2, you could have 1/2 and minus 1/2. You can't have 0 in the middle because you have to go up in steps of a full h bar. And so the only way to do that is to go from minus 1/2 to plus 1/2. And that's what kind of a thing electron is. It's a half integer spin particle. Photons are spin 1 particles. And so they can have, you'd think they would have an M of -1, 0, and 1, but for complicated reasons, which I don't even understand and we're not going to talk about, you can't have an M equals 0 photon because it doesn't have any mass. And so you can have 2 kinds of photons. We might call them spin up and spin down, if we know what direction the angular momentum of the photon is in. But they are S equal 1 spin particles. Protons and neutrons, those are the next ones. We might as well know what those are. Those are spin 1/2. So they can have M equals minus 1/2 and plus 1/2. These 2 kinds of particles are called fermions and bosons. We mentioned those briefly before. All particles that have half integer spin H bar over 2, spin a half, 3 halves H bar, be spin 3 halves. Now all of those particles with half odd integer spin are fermions. They're antisocial, and you can't put 2 fermions in a system with the same quantum numbers. Bosons have integer spin, 0, H bar, spin 1, 2 H bar, spin 2. And this makes them social. They like to crowd into the same quantum state. And this is what photons do. They join together in unison, which is what makes a laser possible. You can't make electron beams into lasers. They don't like each other, and they won't sit there and all do the same thing the way photons do. Okay, these are all the ideas we need to build a periodic table and to understand a little bit more about radiation from atoms. So here we go. This is the periodic table, and the rows of the periodic table correspond to the principal quantum numbers. So that top row that has hydrogen and helium in it, that's the n equal 1 row. The row with lithium, beryllium, and then boron and all these biologically important atoms, carbon, nitrogen, oxygen, that's the n equal 2 row. Sodium is in the n equal 3 row. Potassium, that's K, that's n equal 4. Rubidium is n equal 5. Cesium down there is n equal 6. And the 7th row is n equal 7. Okay. Corresponding to these n's, you can have different L's. The L can go from 0 up to n minus 1, so you might have some S states, that's L equals 0, P states, that's L equal 1, D states, that's L equal 2, and F states, that's F equals 3. L equals 0, 1, 2, and 3, because you can have all the ones below 2. So we'll practice this in a minute, and you'll see how it goes. Okay, so here we go. The S equal 2, the S states, are the first 2 vertical columns of the periodic table. There are 2 of them because the S state has a quantum number of L equals 0, so you'd think you could only put 1 electron in there because that's one state. But the spin of the electron could be either up or down in that L equals 0 state. And so there are 2 possibilities. So you can have 2 electrons in the S level, and all those elements in the first 2 columns correspond to having either 1 electron, the ones on the left, or the two electrons, that's the second column, beryllium, magnesium, calcium, etc. Those guys have 2 electrons in the S level. Now, there is something kind of funny that happens here. Helium really sits on both sides of the periodic table, but it behaves more like the column 8 elements than it does like the column 2 elements. Electronically, it's like column 2, but chemically, it's like the far right side of the periodic table over there on the far right. And so it's traditional to put it over there because it's chemically similar to neon, argon, and krypton. Okay, that's the n equal 1 row. You have hydrogen, 1 electron, helium, 2 electrons, in the n equal 1, L equals 0 state. Okay, now let's go to the second row. The second row is n equal 2, and so you can either have L equals 0 or L equal 1. The L equals 0 states are lithium and beryllium. Those are the S states, and then you'd expect to find the L equal 1 states. And the L equal 1 states can have M's of -1, 0, and 1. That's 3, but each one of those can have 2 electrons in it because they could be spin up or spin down, so that makes 6. And those are the 6 elements over there on the right side: boron, carbon, nitrogen, oxygen, fluorine, and neon. Those are the 6 p states, 6 atoms that have their p state electrons in them, and boron has 1 p state electron, and neon has all 6. and they differ by how many electrons they have in their p states. Okay, well, you know the drill. You should go to the third row then, right? N equal 3. The N equal 3 row is the row with sodium and magnesium. And with N equal 3, you should expect to see L equals 0, 1, and 2. So you should see 2 columns on the left. That's for the L equals 0 part. You should see 6 on the right. Those are the L equals 1 with M equals -1, 0, and 1 for 6 states. So those are there. But what's missing is the 10. You should have L equal 2, which would correspond to M equals -2, -1, 0, 1, and 2. That's 5 states times 2 electrons in each one, because the spin can be up or down. There should be a bunch of elements with 10 of them in a row on that third row, and they're missing. There's nothing there. Well, how come? Well, the reason is that those states, those D states, at the L equal 2 states, they are very wiggly, and it forces the electrons to come close together, and they repel each other, and it pushes those energy levels up to higher energies, up to energies similar not to N equal 3, but like the N equal 4 row. And so that whole row just moves up to the N equal 4 row, and in the N equal 3 row, where we would have expected to see 10 elements for the D states, we don't have them. If you now go to N equal 4, now you have L equals 0, 1, 2, and 3. You can see you have the 2, the S states on the left. You now have the D states that were missing, but those aren't 4D states, those are 3D states: scandium, titanium, vanadium, chromium, manganese. And then you pick up the P states on the far right: gallium, germanium, astatine, selenium. Those are the 3 P states. And that continues on to the 5 row. In the 5 row, you have S states. You have the 10 D states across the middle. You have the P states on the right. So it's 5S, 4D for yttrium, zirconium, niobium, molybdenum. And then you pick up the 5 P states for indium, tin, antimony, tellurium, the ones over there on the right. When you go to the 6th row, this pattern of having the D states pushed up one level has taken a new turn. You might have noticed as we went down, when we got to the 6th row, or one of those rows, 1, 2, 3, 4, should have been D there. I guess the 4th row, yeah, the 4th row should have had some L equal 3 in it. And L equal 3 would give you M's of -3, -2, -1, 0, 1, 2, 3. That's 7. 2 times 7 is 14. You'll notice that those 14s are all missing until you get clear up to row 1, 2, 3, 4, 5, 6. And so the F states have been pushed way up to high energy as well. And the first one of those shows up in row 6. And you see those. Oh, there's the 10 D states. And then the F states are down here in that extra row of the periodic table that they show you, which is at the bottom and nobody wants to think about. The way that works in that row, it says lanthanide series. If you count how many elements are in that row, there are actually 15. The first one goes there where the purple arrow shows. It's the first of the D states on that level. And then the 14 that are left, they're the F states, and they come in all the way across the periodic table, and you pick up the D states: hafnium, tantalum, tungsten, osmium, iridium, platinum, gold. That's a pretty fancy row, that 6th row. That's where you go get engaged, right there, along with carbon from the 2nd row to make the diamond. But the truth is that green lanthanide row and all of those yellow D states in the 6th row, they get all mixed up together with each other, and it's just a mess. And making simple rules about who's got what kind of electrons in what states. Once you get out to the 5th, 6th, 7th row, it doesn't work very well. People have figured it out by doing experiments, but it's not a simple story that you can tell. It's pretty ugly. And then the last row, the one that's got uranium and plutonium in it, that fits into the 7th row the same way the lanthanide row fits into the 6th row. And that, ladies and gentlemen, is the periodic table. So now atoms have new names. Hydrogen is 1s1, helium is 1s2. Can't have 1s3, so lithium has to be 1s2. Its s states are filled, and then it's got one electron in its n equal 1 states are filled, and one of its n equal 2 states is filled. Beryllium has both s states filled, both 1 and 2. If you move to boron with 5 electrons, the 1s level is filled, the L equals 0 part, the s part of the 2 level is filled, and you can put 1 electron into the L equals 1 state, the p state. If you come up to carbon, now we have a new problem. Carbon should be 1s2, 2s2, 2p2, but which of the p states does this go into? Because there are 3 of them. There's m equals -1, there's 0, and there's 1. So there's 2 ways you could do this. You could put the second electron in the same m, say it's -1, and just have it point the opposite way. We say 1 is up and 1 is down. Or you could put it in the next one up. You could have an electron in the -1 state, and you could have an electron in the 0 state. Which is it? Well, a German guy named Hund figured this out, and it's B. So as you put electrons in, they fill up the separate m levels first, and then when you put more in, then they start going in opposite to the electrons that are already there as you fill it up. And you have a homework problem that'll force you to grapple with this, and it's easy, and you'll make sense of it. All right, well, let's talk through the periodic table a little bit. You can go to Wikipedia, and I recommend that you do this. Get a periodic table up on your screen, or maybe you've got one printed. Pick an element at random. Don't go clear up in rows 5, 6, and 7. Keep it simple, down in 1, 2, 3, and 4. Pick an element and look at it in Wikipedia. Over on the right side of Wikipedia, there'll be something called electron. And so if you look up sodium and look for electron, it says 3s1. It has more electrons than 1. And the reason that it says 3s1 is that it's assuming that you know that the n equal 1 and the n equal 2 rows are already completely filled. And so it doesn't even need to tell you about those. It only needs to tell you where the new electron went beyond the first and second rows. And so what this is telling you is that sodium is in the n equal 3 row, and that the electron goes into an s state, and there's 1 of them. You can look up, so there's sodium right over there. 3s1 in the 3rd row, 1 electron in an s state. You might look up nickel. Nickel says it's 4s2, 3d8. If you go looking for nickel, it's in the 4th row. You can always tell that by the 4s at the beginning of an electron configuration. It's in the 4th row, and it's got 8 electrons in the d states. And so it's right there. There are 10 d states, and that's where nickel fits. Right there. And you can look up any element and find out where its electrons are placed. You might be wondering why the periodic table doesn't go on forever. I mean, you can play this game forever. You can go to n equal 8, n equal 9, n equal 10. It gets really wild then. You get to have lots and lots of states, and the table gets really, really big. But we don't do that. It goes to 92, and those are the natural ones. We can make some in particle accelerators and nuclear reactors, but even there we can't go past about 120. Where are all these other elements? Well, the answer is that the electrons would be just fine with it, but the nucleus is the problem. You can't get nuclei to hang together. You can't get protons and neutrons to live with each other. beyond about 100 protons. It just won't go. And we'll talk about that next time. Now here's another piece of funny business that happens with the emission of light from atoms. So far, it looks like if you were in an excited energy level, that you could drop to any lower energy level you like and emit a photon. That turns out not to be true because photons are spin 1. They have 1 unit of angular momentum. And so in order to conserve both energy and angular momentum, in the transition that your electron makes from high energy to low energy, the L has to change by either +1 or -1. That way, the photon's frequency can be just right to conserve energy as the electron loses energy in going down to a lower energy level. And the atom changes its angular momentum by 1, so that when the photon leaves with 1 unit of angular momentum is conserved. So this means, for instance, you can't have a transition from a 4s state to a 3s state, because S has angular momentum 0, and if you go from 0 angular momentum to 0 angular momentum, you cannot emit a spin 1 photon with 1 unit of angular momentum. It wouldn't conserve angular momentum, and so that transition, we say, is forbidden. Can't happen. Well, there are many more rules, and this theory is complex and beautiful, but I think that's probably enough for now. You've got to be exhausted. But before I go, there's an important pattern here, which we'll see again in the days to come. If the system has high energy, quantum system, it can change to a lower energy state, but to do it, it's got to have some help. If there were no such thing as a photon, you might be able to excite an atom to a high energy state, but it would just sit there forever without a photon to take the energy away and allow it to come down. You wouldn't have any way for it to get to a lower energy state. So the photon mediates this transition. It makes it possible. And the photon is a boson. This turns out to be enormously important. There's a general rule of the universe that we've discovered. Particles with high energy, or quantum systems with high energy, either one, can drop to lower energy if there is a boson to help them do it. The spectacular example of this is the muon. A muon is a fermion. It's really just like the electron, only it's 207 times heavier. But E equals mc squared means that if you have more mass, you have more energy. So the muon, you might think of it as an excited state of the electron. It's like an electron, but it's got way more energy because it has more mass. So maybe it could decay into an electron if there were a boson that could do it. And we have found one. It's called the intermediate vector boson, W-, of the weak interaction. It makes this possible. And so this is a reaction that actually takes place in nature. This is how muons disappear. A muon, a mu-, muon with negative charge, decays into an electron with negative charge, plus a couple of neutrinos. And we're going to have to talk about those things later. They've been thrown in. I don't know what these particles are doing here, but they're there. We can detect them. And this is what the decay looks like. You'd think if you looked at this, you'd see a W- coming out, like you'd see a photon coming out of an electron decay. But the problem is that the W- decays into an electron and an anti-electron neutrino in about 10 to the minus 24 seconds. And so nobody cares about the W- boson, except that it makes this decay possible. It's the existence of the W- boson that makes it possible for muons, which are like heavy electrons, to turn into normal electrons. That boson mediates the interaction. And it looks like the whole universe is built this way. The universe is built out of particles, and then there are force or interaction bosons. These bosons make it possible for particles to push on each other and to decay to lower energy or mass states, which can be completely different particles in particle physics. The boson for electrons in the electromagnetic interaction is called the photon, and the force that the photon corresponds to is just the force of electricity and magnetism. Every time you pull your slinky clothes out of the dryer and they crackle, you are hearing something that's only possible because photons are making electricity, static electricity, possible. And when you hold a magnet in your hands and you push the same poles together and it repels, that force you feel is made possible by the photon, which creates the electric and magnetic fields that make all that pushing and pulling with electricity and magnetism possible. And we'll do more on this in the last few days of class. See you next time.